Alright, good afternoon everyone. We will start here. So today we will be looking at new unit 3. So under unit 3 we are going to be talking about chemical calculations. Now here you learn very important concepts. Actually we are starting with oxidation numbers, but later on one of the most important concepts you are going to be learning about is the concept of mole, right? And then from there onwards we talk about titrations. So we'll come to that at the end, but we have to gradually go up to that level. So molar calculations, which we are going to be discussing at the end, is going to play a major role throughout your chemistry life starting from now. Okay, so keep in mind this lesson is something that you can't miss. It's very important to attend every day. Don't miss out any classes. So today we'll start with the first topic under this unit, which is oxidation numbers. Now I don't know whether you remember when we were talking about polarization of bonds, we discussed oxidation numbers. Can you remember a little bit? We discussed what an oxidation number is and how we actually figure out an oxidation number when it comes to a covalent compound. Can you remember? Like hold the charge separation and how we put the numbers and all that, right? So today we are going to go over that again and make sure that you are completely comfortable with this part. So don't worry, I'll be teaching you from scratch what oxidation numbers are, and then when it comes to rules that are revolving around oxidation numbers, there is a page that is completely dedicated to this. So we will be moving on to that as well, and we'll discuss what oxidation numbers rules that we see as well. So first of all, now we'll start with the simple explanation about oxidation and reduction, because without that you wouldn't sometimes understand what's going on here. So we have something called oxidation and we have reduction. Now there are many definitions for this, but the most important one over here when you're talking about oxidation numbers of different elements in a compound is that you need to remember, if electrons are lost, right, what happens is an oxidation. So losing of electrons are referred to as oxidation, and gaining of electrons is referred to as reduction. Losing of electrons are referred to as oxidation, gaining of electrons are referred to as reduction. So now if you take an element like sodium, we know it can lose, we actually normally talk about these things in gaseous state. We know about ionization energies. So let's say if you take sodium atoms, and if a sodium atom loses one of its electrons, or the outermost electron it has, we form +1 sodium ion. So this is an oxidation that has taken place, right? So over here the charge we see on this particular ion is referred to as its oxidation state. The charge we see on this ion is referred to as its oxidation state. So we can say sodium is in +1 oxidation state. So basically students, oxidation and reduction is understood. Oxidation number refers to the charge an ion would have, or charge a specific atom would have after removing electrons or gaining electrons, right? Very simple. Oxidation number means the charge a specific atom would have after gaining electrons or losing electrons, one of the two. Here in this case it has lost an electron and gained a +1 charge, So the oxidation number of this particular ion right now is +1. Is that clear? Now, what about this atom over here? Does it have a charge? Does it have a charge? Does it lose electrons, gain electrons? Does it even share electrons anywhere? No. So therefore, this atom does not have an oxidation number, plus or minus oxidation number. It's said to be having a 0 oxidation number. Any atom that is not taking part in any bonding, or any atom that has not necessarily given electrons or gained electrons, usually have oxidation number of 0. Okay. Apart from that, when it comes to certain molecules, like for example chlorine, hydrogen, molecules that are bonded to itself, right? Basically, students, here their electrons are evenly shared, no? Because of that, there is not going to be any oxidation number differences between the two atoms. Both of them are considered to be 0 in oxidation number. Is it understood? Right? So basically, elements in general, we say are having 0 oxidation number. Is that clear? So now if you take chlorine over here, if you take chlorine, a gaseous atom of chlorine can gain an electron and turn into chloride. Right? Chloride. So here this is a reduction, gaining of electrons. This is the reduction. So after gaining the electrons, it becomes -1 in oxidation state. Is that clear? Do you understand? So it is a -1 charged ion. So therefore it's -1. Now if you are talking about aluminium, so aluminium turns into aluminium 3 plus, releasing 3 electrons. Aluminium 3 plus releasing 3 electrons. So therefore, what is the charge of this aluminium? It is +3. Oxidation state is also +3. Is that clear? Over here, let's say something like nitrogen. Nitrogen atoms can take 3 electrons and form nitride ions. Right? I'm taking 3 electrons because it's a large number of electrons to be taken. Right? So just want to show you that. So when it comes to this particular ion, the charge is -3. So their oxidation state would be -3. Is that clear? Is that understood? So when it comes to ions like this, we say monoatomic ions, ions that are made up of only one atom. Those ions, the oxidation number is super easy to figure out. Their charge is the oxidation number. Their charge is the oxidation number. Is that clear? Right. So this is how we actually figure out the charge of a monoatomic ion, or oxidation number of a monoatomic ion. Apart from that, students, if something is increasing in oxidation number, if I draw it over here. Now if you talk about sodium, sodium was here at 0 oxidation number, aluminium was also here, right? Chlorine was here, nitrogen was here, everyone was here, right? 0 oxidation state. Now sodium went to +1 oxidation state. Aluminium went to +3 oxidation state. So sodium is now here as sodium plus, aluminium is now here as aluminium 3 plus. So this is an increase in oxidation number. Is that clear? An increase in oxidation number is generally referred to as oxidation. If someone is saying this particular chemical underwent oxidation, that means there was an increase in oxidation number of those elements or atoms. Is that clear? If we say the oxidation number decreased from, let's say, when it comes to chlorine, it became chloride 1 minus, right? And then nitrogen became nitride 3 minus. So there was a decrease in oxidation number. So decrease in oxidation number is usually referred to as a reduction, right? Decrease can only happen through the gaining of electrons. So therefore we say if the oxidation number is reducing, we say it's a reduction. Is that clear? So imagine there was aluminium 3 plus. Someone gave aluminium electrons and aluminium 3 plus became aluminium metal, let's say, going from here to here, plus 3 to a solid. So what is that? Oxidation or reduction? Reduction. Goes from plus 3 to 0. Is it understood? So this is basically what you need to remember when it comes to oxidation and reduction. So take your tubes out. So here we have given you some information about oxidation as well as reduction. So turn to page number 2, please. Turn to page number 2. I will turn back to page number 1 in a second, but I want you to have a small detail that is important. So oxidation number, also known as oxidation state, is a numerical value assigned to an atom with within a molecule or an ion to represent the hypothetical charge it would have if electrons were transferred completely during the formation of that species. Oxidation numbers are used in redox reactions to track the flow of electrons, right? So increase of oxidation number shows oxidation, decrease of oxidation number shows reduction. So I want you to highlight certain parts of this page because that is important. Please highlight this. That is this. It's a numerical value assigned to an atom within a molecule or an ion. Within a molecule or an ion to represent the hypothetical charge it would have if electrons were transferred completely during the formation of that species. If electrons were transferred completely during the formation of that species. Let me explain that part. If electrons were transferred completely during the formation of that species. Let me explain that specific sentence. Now that sentence is not very applicable to monoatomic ions because monoatomic ions are basically anyway completely transferring electrons. Monoatomic ions. So when it comes to monoatomic ions, students, its oxidation number is basically the number of electrons it has released or gained when forming the ion. So in other words, its oxidation number is the charge itself when it comes to monoatomic ions. For example, if you take chlorine, it's having oxidation number of -1. If you take oxide, its oxidation number is -2. If it is, let's say, magnesium, magnesium ions form +2 charged ions, so its oxidation number is +2. Basically, monoatomic ions mean ions consisting of one single atom. So their basic charge is their oxidation number. Simple as that. However, when it comes to molecules, now molecules don't actually have full electron transfer. So students, for example, if you take molecules here, if you take something like HCl, right, can we talk about electron transfer here? Is hydrogen and chlorine transferring electrons? Electron transfer means, imagine I have this, I give completely one to another person, or maybe both of them to another person. That's a transfer of electrons, right? Taking one electron out and giving it away. Sharing is a different thing. No? Sharing doesn't mean giving away, no? Right? Like, donating and sharing are two different things, right? Just like that. So transfer is different. Transfer means completely giving away or completely receiving whatever someone is giving away. Sharing means like the electrons that are forming a bond is basically still between these two. They both still lay claim to these two electrons. Basically, the bond electrons belong both to hydrogen as well as chlorine. Electrons have not gotten transferred to one. Is that clear? But the thing is, when you are forming a molecule, if it is forming a covalent bond, if the covalent bond is formed between similar atoms, like for example identical atoms like this, then we can be guaranteed that the bond electrons, imagine these are the bond electrons, these bond electrons are present right in the middle between these two atoms. Can someone tell me why that is? Can someone tell me why the electrons are present right in the middle between the two? So there is not a full transfer of electrons, we say partial transfer of electrons. Like electrons are going very close to chlorine, still shared, but very close to chlorine. Is that understood? So because of that, in the paragraph that we read, see, it says it's a hypothetical charge a molecule or atoms in a molecule would have if electrons were transferred completely during the formation of that species. If electrons were transferred completely, meaning students, now there is a partial transfer now. Over here we expect the hydrogen and the chlorine electrons to be right in the middle, right? These are bond electrons. I'm using dot cross diagrams to show that. But we know since chlorine has a higher electronegativity, the electrons are attracted more towards chlorine. Like it gets slightly closer to chlorine. So we can think of this as a partial transfer of electrons, or electrons are getting closer to one side than the other. So what they say here is, just imagine if both these electrons were given to chlorine. If both of them, these electrons, were not just shared, not sharing, but what happens if both of them were actually given to chlorine? Then what would happen? Then what will be the charge of chlorine? Can someone tell me? If both of these electrons were directly given to chlorine, what will be the charge of chlorine? Minus 1 or minus 2? Minus 1 or 2? 1. Yeah, why would it be minus 1? Correct, minus 1 is correct. Why? Because out of these two electrons, one electron anyway belongs to chlorine. The other electron is the electron that hydrogen contributed to the bond. Do you understand? So that electron is additionally coming to chlorine. Is that clear? Imagine I put an electron, hydrogen puts an electron, I take both of them. So one electron was anyway mine, and then I am taking hydrogen electron along with it. So then I am gaining one additional electron. So therefore this becomes minus charge. So they are saying if this happens, the charge it would have is referred to as its oxidation state. This, like imagine they say if this was an actual complete transfer of electrons, chlorine might have been minus 1, and since hydrogen is losing its electron, it will be plus 1. Do you understand? When it comes to a covalent bond, there is no complete transfer of electrons. There is only sharing, but not even sharing. No. If the electronegativities are there like this, is that clear? So because of that we say, if this type of partial sharing is happening, we ask ourselves, what if this is not a partial sharing? What if this was a complete exchange? Then what would be the charge on chlorine here? Then what would be the charge on hydrogen here? You ask yourself that question, right? So then you can figure out, okay, this is minus 1, this is plus 1. Is that clear? Now that brings us to a very interesting point, that is, whenever a bond like this is polarized, we know this one is more electronegative, the electrons are attracted to this side, so we just usually write delta minus here and delta plus here, right? So basically, if you are assuming electrons have been completely transferred, this is going to be having a -1 oxidation number, this is going to be having a +1 oxidation number. Is that clear? So the partial charges in your head, you can convert them into +1, -1. Is it understood? Is that clear? So this is oxidation number. This is oxidation number for molecules. Now we call this a hypothetical concept. Why is it a hypothetical concept? Because I just asked you, how many times did I ask you to imagine? Right? Because we have to imagine. Right? This is not necessarily actually transferring electrons. Hypothetical concept means, now I told you that day as well, I will repeat the same story. When it comes to ions like this, it's very clear cut. It's very clear cut. Chlorine gained electron. When it comes to this ion, oxygen gained 2 electrons. Magnesium has given 2 electrons. It's very clear cut. They exchange, transfer. But when it comes to molecules, it's not very clear cut, because they don't transfer electrons. They are sharing electrons. Right? So therefore, we have to come up with a new way to assign them a charge. Like we have to say, okay, I want to figure out what would be the charge they have if they had transferred electrons when forming this. So then, since it's not a real thing that is happening, we develop this new concept, understanding, called oxidation number. It's a hypothetical concept. We think if these bond electrons were given to the more electronegative element, what would be the charge there? Since these electrons are given to this one, this hydrogen is going to be having a lower number of electrons, so what will be the charge here? So the charges that they obtain is referred to as the oxidation number. Is that clear? Right. So when it comes to these kind of similar atoms joined together, their oxidation number is still 0. Nothing new there, right? Because these electrons are not going close to one or the other, no? They are right in the middle. There's no partial transfer of electrons. Is that clear? So because of that, it's not necessarily having any different oxidation number. I will do one more example, then I'll give you some questions and I'll give you time to write this down. We'll take something like water. Right, water. Now I would recommend you think of polarization, because you all are now very good with polarization. As far as I can remember, when we did questions in class, you all were very good with polarization. So think of how each of these bonds are polarized, right? Oxygen is more electronegative, right? So out of oxygen and hydrogen, is hydrogen or oxygen more electronegative? Oxygen. So therefore the bond electrons are attracted more towards oxygen. So when you are considering this bond electrons, there's a partial transfer of electrons towards oxygen. So if we wrote polarization, we write delta minus here, delta plus here, no? Right? Instead of writing delta minus, delta plus, just think, if we completely transfer these electrons to oxygen, what will be the charge on oxygen? If I transfer both electrons here, oxygen will be -1. And what will be the charge on hydrogen? +1. Is that clear? So similarly, there's another bond like that. So we have to do the same there. Hydrogen, oxygen. If I transfer both the electrons to oxygens, because now why would I do that? Because oxygen is more electronegative. Electrons are anyway attracted towards oxygen. So instead of a partial transfer, we can think of it as a complete transfer. Both electrons are given to oxygen. So therefore, this will be +1, this will be -1. Is it understood now? Is that clear? 100%? So now, what is the charge on hydrogen? What is the charge? +1. So oxidation state on hydrogen would be referred to as +1. Each hydrogen is +1. Right? This one is also +1. Don't add them together and say hydrogen is +2. Okay? We say oxidation number for individual atoms. We say oxidation number for individual atoms. We don't add the atoms together usually and say that. Is that clear? There are certain instances we talk about something called cumulative oxidation number. I will explain that later. But when it comes to like 99.9% of the time, whenever you are talking about oxidation number of an atom, we talk about its charge, individual atoms charge. Okay, you can see both hydrogens are +1. So if someone asks what is the oxidation number of hydrogen in water, you say +1, not +2. Okay. What about oxygen? What is the oxidation number of oxygen? -2, because from this side it is gaining an electron, from this side it is gaining an electron. So therefore it is gaining 2 electrons from 2 bonds. So therefore overall charge over here will be -2, right? So oxygen would be -2 in charge. Is that clear now? Right. So take your writing books out. Take your writing books out, please. Take a new heading. Write down. Take a new heading, Unit 3, Chemical Calculations. Unit 3, Chemical Calculations. Under that, take another subheading, Oxidation Numbers. When it comes to monoatomic ions, the oxidation number would be the same number, or would be the same number that is seen in its charge. Example, can you take this down? These ones, right? Then write, after that please write, when it comes to molecules, complete transfer of electrons between atoms, are not seen. Complete transfer of atoms between atoms are not seen. As a new point, write this as point, different points. As a new point, write, however, there is a partial transfer of electrons bond electrons. Can you correct that? Partial transfer of bond electrons towards the more electronegative element, when two atoms with different electronegativities are bonded together. Alright, are we done taking that down? Did you miss something? Okay, right, so then write, if we consider this partial transfer if we consider this partial transfer to be a complete transfer, if we consider this partial transfer to be a complete transfer, then we can obtain the hypothetical charge each atom will have. Then we can obtain the hypothetical charge each atom will have. Can write, then we can obtain the hypothetical charge each atom would have. Then you can write that charge is referred to as its oxidation number. That charge is referred to as its oxidation number. Take this down. Take this down. Take only HCl down. We'll do some examples after that. So the first sentence reads, since chlorine is more electronegative, the electron pair is attracted towards chlorine. Within brackets is partially transferred. Attracted or partially transferred towards chlorine. And when it comes to the next part, right, so these are the oxidation numbers of hydrogen and chlorine here, and then I have indicated if the bond electrons were completely transferred, this would be the charge on each atom. So these are the charges on each atom if the electrons were completely transferred, but they were not, right? That's why we use the word if. Okay. Finish copying it down fast. Let me know when you're done. All right. So now we move on to a small question. And there we can take down water as well. So take down a small question in your writing books itself. Find the oxidation number find the oxidation number of each atom. Find the oxidation number of each atom in the following molecules. In the following molecules. Find the oxidation number of each atom in the following molecules. So we'll start with H2O. We have already done it, right? Then we'll go to ammonia, NH3. We'll do simple ones, carbon dioxide, right? Apart from that, we have something like, let's say, sulfur trioxide, SO3, sulfur trioxide, and I would like for you to do this as well. 5 CH4, 6 CHCl3. Okay, so for the time being we'll go ahead with the 6 because we will be doing this a lot today. You will need to get comfortable with Lewis structures. Hopefully you remember the Lewis structures of each of these, because that is important. Otherwise you can't get to the electronegative, sorry, you can't get to the oxidation number of each of these. And students, before you start answering, please listen. Again, for single monoatomic ions, we don't actually need the phrase oxidation number. It's basically we are talking about electron transfer. Electron transfer is evident when you look at the charge. It's just the charge you have to look into. For a single monoatomic ion, if you take a look at this charge, you see 1 electron gain, 2 electrons gain. You look at the charge, it is clear to you, right? You don't have to talk about something called oxidation number. We need actually the oxidation number concept mainly when it comes to covalent compounds and polyatomic ions, because covalent compounds, there is no complete transfer of electrons, right? So scientists needed to talk about like what kind of charge they would have if the electrons have gotten completely transferred. That's when they introduced oxidation numbers. Is that clear? So here then, when we are talking about oxidation numbers, like the charge they would have if the electrons are completely transferred, they incorporated the ions, monoatomic ions as well. So in the monoatomic ions also, the charge they have directly is equal to the oxidation number. Then we talk about polyatomic ions. We'll come to polyatomic ions once you have mastered the molecules. We'll first go through the molecules and see whether you can get to the answers. After that, I will give you a question on polyatomic ions. Let me quickly get to the answers here. I hope you did nitrogen dioxide as well. So we'll do one at a time, students. We'll start with water again. I want to make that point very clear to you. So we'll start with water. Oh, there was CH4 there, right? So now if you take water, we know these bond electrons are not necessarily evenly shared. It is going to be mainly attracted towards towards oxygen. So therefore oxygen over here gets a like a partial transfer of electrons. If it was a full transfer, oxygen will be -1. So this hydrogen will be losing an electron, so therefore it's +1. Same story can be said about this bond, because they are both similar bonds. So therefore oxygen's oxidation number is going to be -2. Hydrogen's oxidation number happens to be +1. Is that clear? And then when it comes to ammonia, NH3, nitrogen is more electronegative than hydrogen. Now students, the Lewis structure should be very simple to you. I don't want to spend a lot of time explaining how the Lewis structure was obtained. We have drawn ammonia like a million times, right? None of you got ammonia wrong, but some of you got SO3 wrong, right? That is a problem, right? So now anyway, hydrogen is less electronegative than nitrogen. So this bond electrons are attracted more towards nitrogen, so therefore nitrogen is -1, hydrogen is +1. Right? Whenever bond electrons are attracted to one atom, it doesn't matter which two atoms are involved. If electrons are attracted to one atom more than the other, the atom that electrons get attracted to more gets -1. The other one gets +1. Simple. So that happens when it comes to each and every bond. So there are 3 bonds here. So this bond is again +1, this side is -1, -1, +1. Is that understood? So therefore students, if you count the number of negative charges around nitrogen, -1, 2, 3. So what is the oxidation number of nitrogen? -3. And hydrogen, each hydrogen is +1, so we don't write like +1 all together, added together +3. No, we write the oxidation state of one atom. Each hydrogen atom here has +1. Is that clear? Each hydrogen is +1. Over here we added these negative charges because all these negative charges are present on one atom, a single atom, right? These are 3 different hydrogen atoms. They each carry +1. So hydrogen is +1 in oxidation state. Don't add them together and write +3. +3 is present on 3 atoms now. One atom is +1. Is that clear? So nitrogen is -3. Actually, all of you wrote this one correct. That's fine. And then carbon dioxide. What happened? Carbon dioxide. Some of you wrote that one wrong. If you take carbon dioxide, maybe that's because we are encountering double bonds for the first time here. We know compared to carbon, oxygen is very electronegative, right? Carbon is 2.5, oxygen is 3.5. 2.5, 3.5. Is that clear? So now, if you consider each bond separately, these bond electrons are attracted more towards oxygen. Now let's take individual bonds. So this first bond here, those electrons are attracted towards oxygen. So therefore oxygen gets -1. If they were completely transferred, oxygen will get a -1, carbon will get a +1. But keep in mind, there's another bond here. That bond electrons are also attracted towards oxygen. So therefore again oxygen will get a -1, carbon will get a +1. Do you understand? Each bond should be separately considered. So on oxygen there is a -2 charge, but then we have 2 other oxygen carbon bonds. Again this bond is also giving electrons more towards oxygen, so oxygen is -1, carbon is +1. These bond electrons are also given to oxygen, so therefore -1, this side is +1. So around carbon, the oxidation number of just carbon atom, you can see carbon has 4 positive charges. Single carbon atom has 4 positive charges, so therefore it is +4. Each individual oxygen atom is carrying 2 negative charges, so therefore oxygen over here is -2. Is that clear? Now we usually indicate it, students, like this. We draw a small line and then we draw arrow pointing downwards and write -2. That's how we normally do it, right? Because sometimes in certain atoms, for example when it comes to hydrocarbons and all that, there can be 2 carbons that are close, in a similar carbon chain. They can have different oxidation states. So then writing it like this would be difficult. So then what we do, at individual carbon atoms we draw a line and write their oxidation number, right? Okay, so these are the oxidation numbers of carbon and oxygen. Now sulfur trioxide, I said sulfur trioxide. This is the Lewis structure, right? This is the Lewis structure. Now sulfur is less electronegative than oxygen. Oxygen is the second most electronegative element in the entire periodic table. So therefore students, if you take oxygen is going to be more electronegative, so these bond electrons are mainly towards oxygen, so oxygen becomes -1, sulfur becomes +1. and again these bond electrons are more towards oxygen, so this bond also -1 +1. So that same thing happens to all the other bonds as well. Oxygen side is -1, there are 2 bonds, +1 +1 because there are 2 bonds around, so 2 bonds between oxygen and sulfur in each case. So this -1 -1 +1 +1, each bond is having its electrons more attracted towards oxygen. So therefore students, around this sulfur, the total number of positive charges how much around the sulfur? 1 2 3 4 5 6. The oxidation number is +6. Okay, if you take a look at all of the oxygen, all the oxygens usually have a -2 oxidation state. Is that clear? Oxygens are -2, sulfur is +6. Oxygen is -2, sulfur is +6. Right, so if you want to write it separately, you can do. You can write sulfur is +6 in oxidation number, oxygen is -2 in oxidation number. So we write the oxidation number of one atom, okay? We don't add them together, all 3 oxygen atoms, we don't add. One atom's oxidation number is written. So the last 3, we have CH4. Can you all remember the electronegativities of hydrogen and carbon? You should be by now. Carbon is 2.5, hydrogen 2.1, 2.5, right? It will be helpful. So that means carbon is more electronegative. Hydrogen is 2.1, carbon is 2.5. So that means these bond electrons attract more towards carbon. Is that clear? So therefore this bond is minus towards the carbon side and plus towards hydrogen. So that's the same story for each carbon hydrogen bond. -1 +1, -1 +1, again -1 +1. So the oxidation number of carbon happens to be, there are 4 negative charges, happens to be -4. Hydrogen is +1. Is that clear? And lastly, we move on to not lastly, I asked you to do nitrogen dioxide also, right? Did you do it? But before we do, we'll write CHCl3. CHCl3. Can someone tell me the electronegativity of chlorine? What is the electronegativity of chlorine? 3.0. 3.0. So we have hydrogen, if I just write them down, hydrogen has 2.1, carbon 2.5, chlorine 3.0. So chlorine is more electronegative than carbon. So this bond electrons are going more towards chlorine. So chlorine will gain -1, carbon will be +1. Same bond here. So therefore chlorine -1, carbon +1. Same bond here as well, right? Chlorine -1, carbon +1. Carbon hydrogen bond, however, carbon is more electronegative. So therefore carbon hydrogen bonding, carbon gets -1 because the electrons of carbon hydrogen bond goes to carbon and hydrogen becomes +1. Is that clear? Is that understood? So therefore students, if you take a look at carbon now, around carbon there are 1 2 3 plus charges and 1 minus charge. So the total oxidation number is +2. Did you see that? Right, because +3 plus -1, +3 plus -1. Basically that means +3 minus 1. Right, so the value is +3 minus 1 is -2. Not sorry, +3 minus 1 is +2. right? Like what we have written here. And then we have hydrogens, which is basically +1, and chlorine, which is basically -1. Are we okay with this part? Okay, I believe I didn't give you time to do nitrogen dioxide. Quickly do it. Tell me what is the oxidation state of nitrogen. So right, when you draw the nitrogen dioxide molecule, you have a odd number of electrons there on nitrogen. Hopefully you remember this. Hopefully you remember the odd number of electrons part. Right, so you have nitrogen like so. If I draw all of the electrons in this case, this oxygen has 2 lone pairs, this oxygen has 3 lone pairs and a negative charge, and this nitrogen has 1 lone pair, like 1 unpaired electron like this, along with a positive charge. Is that clear? So now let's see how we get the charges here, right? This is the Lewis structure of nitrogen dioxide. It has a formal charge on nitrogen as well as oxygen. So this oxygen nitrogen bond, oxygen is very electronegative, not very actually, oxygen is 3.5, nitrogen is 3, right? So therefore oxygen is electronegative compared to nitrogen. So the bond electrons of this nitrogen oxygen bond goes to oxygen. So therefore this is -1, this side is +1. Is that clear? -1 +1. So we can say the same about these bonds. This is +1, this is -1, -1, +1. So if you take a look at this oxygen, overall oxidation number is -2 because there are 2 negative charges. Here there's 1 negative charge that we obtained through the bond electrons, and there was already a formal charge, -1. So this oxygen is together -1, and this -1 will become -2. So the oxidation number on this oxygen is -2. What I'm trying to show here is, if the atom already has a formal charge, we have to add that to the charge that we get from the bond electrons, right? If the bond electrons were completely transferred, we get a -1 here. No? On top of that, we have to add this formal charge here as well. Is that clear? And when it comes to nitrogen, I'm happy to see that all of you have gotten to the correct answer there. At least the answers that I checked. So we have formal charge plus here, which is written in black, and then there's other 3 plus charges that we obtain from, like, thinking that the bond electrons were completely transferred. So there are 3 positive charges over here and 1 positive charge coming from the formal charge, altogether +4. So you can see oxygens are -2, nitrogen here is +4. Is it understood? Nitrogen +4, oxygen -2. Correct. So very good, children. You have gotten to this part, which is actually a good indication. So I believe all of us are comfortable with this part. Now we can move on to the next part. Next part is basically polyatomic ions. You can write a new heading, polyatomic ions. Students, I'm not going to give you anything like any details there, because polyatomic ions basically follow the same, like it doesn't matter when you're using this particular method, it doesn't matter whether we are applying it to a polyatomic ion or a molecule. But still, I know you would want to see this as a separate section. That's why we give it under a separate section. So I will give you a question and I'll explain the answers after you do the question to your best of your ability. So write down a question. Draw the Lewis structures. Draw the Lewis structures of the following polyatomic ions. Of the following polyatomic ions Draw the Lewis structures of the following polyatomic ions. And write the oxidation numbers of each atom. These are the common polyatomic ions that you come across normally. I will give you some uncommon ones as well. Right, students, first of all draw the Lewis structures, okay, because you don't have to step by step show me how you drew the Lewis structures. I want you to get to the Lewis structure. You can do the rough working somewhere and draw the Lewis structure correctly and then get to the correct answer. Can I do till nitrate and then I'll give you some more time to do this? Otherwise, I feel like I'll have to wait a lot of time, wait a lot to see whether you get this one also correct. So let's see if I'll jumpstart your memory about Lewis structures a little bit, especially when it comes to nitrate. I saw some of you have done it wrong. So let me draw these structures. So now if you take carbonate. Now anyone who hasn't learned about Lewis structures, this will be a brilliant time to, or if you have forgotten, this will be a good time for you to remember these parts again, right? So what we do first is, we write down the number of valence electrons of each atom. Carbon has 4, oxygen has 6. Valence electrons refer to the outermost electrons, okay? Oxygen has 6 outermost electrons, carbon has 4. But there are 3 oxygen atoms. So what we do is, since there are 3 oxygen atoms, each oxygen atom brings 6 valence electrons. So 6 into 3 would make this 18. And then this 2 minus charge. 2 minus charge indicates additional 2 electrons being present there. That's why it's 2 minus. Right? When there are 2 additional electrons, it's minus. So therefore, or 2 negative charge indicates there was additional 2 electrons present in this ion. So we need to include those 2 also here. So what we are trying to get over here is the basic valence electrons of the ion. If the valence electron is exceeded, the ion will become negative. If the valence electron number is smaller than what it should be, the entire ion will be positive. That's why if the charge is negative, we add electrons here. So this is the total number of electrons, which happens to be 24. Then we can talk about electron pairs. Right, so we divide this number by 2. 24 divided by 2 is 12. So we have 12 electron pairs. Meaning, students, we need to show exactly 12 electron pairs in the Lewis structure. Is that clear? So there are 2 types of electron pairs in Lewis structure: bond electron pairs and lone pairs. Bond pairs and lone pairs. So the total number of bond pairs plus lone pairs in the entire Lewis structure should be 12. Is that understood? That's why what we write here, total number of bond electron pairs and lone pairs together should be equal to 12. So now when we are drawing this, we first try to figure out the central atom. central atom is the one with the lowest electronegativity, in this case carbon, right? And then we connect all the other atoms to that, like so. So now to connect these atoms to carbon, I have utilized bonds. Each bond represents two electrons, or this is 3 bond electron pairs. I have to represent 12 electron pairs now. Out of that I have already shown 3, so therefore I subtract that, right? Saying bonds. For bonds I have utilized 3 electron pairs, right? To show bonds I have utilized 3 electron pairs. So then I am left with 9 more electron pairs. So I will distribute them to the outermost atoms first, and then if there are any remaining I will give it to the central atom. Starting with the outermost atoms, I am going to complete the octet. Each oxygen has a bond electron pair, that means each oxygen has 2 electrons. I need to complete it all the way up to 8. So bond has 2, that means oxygen has 2 here. Then I am going to give oxygen 6 more electrons so that it has 8. Is that clear? So that is completed the octet. I am just trying to remind you because some of you are getting the wrong answers. So now I have distributed 9 lone pairs altogether. 9 lone pairs. See, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we have to see formal charges. Now formal charges are calculated by seeing how many electrons are there in each atom. Oxygen should have only 6 valence electrons, but this particular oxygen has 6 electrons here, and in this bond there is 1 electron of oxygen. Each bond has 1 electron of oxygen and 1 electron of carbon here. So this bond has 1 electron of oxygen, and this oxygen has 6 electrons outside as well. That means oxygen has 7 electrons. But oxygen's valence electron number is 6. This has 1 more. So therefore oxygen is -1 in formal charge. Each oxygen is like that. So therefore -1, -1. And the carbon over here should have 4 valence electrons. Each bond has 1 electron of carbon. So there are only 3 bonds. That means it has only 3 electrons. So therefore it is missing an electron, so therefore carbon is +1. This is not good. Too many formal charges. What do? You convert 1 lone pair from any of these bonds into a bond pair. So we can convert 1 lone pair like this into a bond pair. I'm just roughly going through the basic rules, okay, of Lewis structures. Now when you do that, the formal charges on those 2 atoms will be cancelling off because there was an additional electron on oxygen. Now it is gone. Carbon gained the electron, therefore plus charge of carbon is gone. This is the Lewis structure of carbonate. Is that clear? Now the rest is simple. This bond, oxygen is more electronegative, so therefore it gets -1, carbon gets +1. There are 2 bonds here. Oxygen is more electronegative, oxygen gets -1 on each bond, carbon gets +1. Here also the same, +1 on carbon, -1 on oxygen. Each of the oxygens is -2. You can see over here also -2. Over here also -2. Each oxygen is -2. This carbon over here is what? What is the oxidation number of carbon? +4. Is that clear? So I'm not going to draw any other structure the way that I did this. I just wanted you to remember the Lewis structures. From here onwards I'll just draw the structure and move on. Is everyone okay with this part? Shall we quickly move on to the next part? I'll erase this. These parts I believe you already know, but I want to be sure. Then we have sulfate. Very simple. SO4 2-. We have drawn this, right? We have sulfur here. We have oxygen sulfur double bonds like this, and then we have, right, negatively charged oxygen atoms here as well. Is that clear? Right. So now, if you take a look at this, oxygen sulfur bond is again, oxygen is more electronegative. So therefore, oxygen has a bit of a, like, electrons are attracted more towards oxygen. So this becomes -1, this becomes +1. Same here, when it comes to any other oxygen, oxygen becomes -1, this side becomes +1. These bond electrons are given to oxygen, so -1 +1. Same here, -1 +1, -1 +1, -1 +1. So now if you take a look at oxygen, each oxygen is -2. Each oxygen is -2. Right, this oxygen as well as this oxygen is -2. You can see -1 formal charge and -1 charge coming from partial transfer electrons is going to be -2. But this sulfur over here, you have +1, +2, +3, +4, +5, +6. Sulfur has a total of +6 charge. Sulfur has a total of +6. You have a question? Right? Anyone has a question? All good, right? So this is +6 in charge. Oxygens are -2 in charge. Can someone tell me why sulfur can have this many bonds? We saw that most of the other elements can't, like period 2 elements and all that can't have this many bonds. But why can sulfur have? It's in period 3. Period 3 or below, like period 4, period 5 elements can have more than 4 bonds. They can exceed the octet, right? They can exceed the octet. We have discussed this why. So just for the time being, I don't want to go into that again and explain, because we have extensively discussed why period 3 elements and below can have extended octet. Okay, NO3, the one that you got wrong. I don't know whether all of you got it wrong, but some of you did. So let's see. Did you get to something like this, students? NO3 Lewis structure? Did you get to something like this? Now why did you stop here? Now some of you I saw have converted, now there are lone pairs on these oxygen, students, I didn't draw them. When you're drawing the Lewis structure, you will see these lone pairs as well. In the previous one also I didn't draw it because I was mainly interested in the formal charge. So now these two have 3 lone pairs each. We could have converted one lone pair into a bond pair and remove these plus minus charges. Why can't we do it? Why can't we just erase this negative charge and erase this positive charge, convert one lone pair into a bond pair? What is the problem? Nitrogen is in period 2. Period 2 elements can't have more than 4 bonds. Very good. So therefore, over here, if you talk about the electronegativities, nitrogen is less electronegative than oxygen. Oxygen is more electronegative. So therefore, bond electrons are going more towards what? Oxygen. So oxygen becomes -1, nitrogen becomes +1. Same to all the bonds here. Oxygen becomes -1, nitrogen becomes +1. So now, what is the oxidation state on nitrogen? What is the oxidation state on nitrogen here? You have to add 1, 2, 3, 4 and there's a formal charge. Altogether 5. So this is the highest oxidation state that we see on nitrogen, +5 oxidation state. Is that clear? Now pay attention. Did you see everywhere that we looked at, the oxygen always gets -2. Did you catch on to that? Everywhere that you see oxygen, you usually see -2. if it is bonded to another different atom, it's minus 2, right? So usually students, going forward I will talk about some rules. After the break I'll talk about some rules. In those rules we say oxygen is always minus 2, and there are few exceptions, and those exceptions are usually referred to as peroxides, superoxides, and when oxygen is bonded to fluorine. So those are the only 3 exceptions. Except for that, that means 99.99% of the time in most of the complexes you see, you don't have to worry, compounds you see, you don't have to worry, oxygen always ends up getting minus 2. Is that clear? If it is bonded to itself, of course 0, but if it is connected to another atom, it is going to be minus 2. Clear? If you are not getting minus 2, then double check whether it's a superoxide, peroxide, or whether the oxygen is bonded to a fluorine. Then only its oxidation number changes. Right. So oxygen over here is minus 2. You can see minus 1 over here, another minus 1 over here, minus 2. Every oxygen here is minus 2. Are we okay with this part up to this? Right. Did any of you do this 3 as well? Phosphorus or phosphate? Can someone tell me what is the oxidation state of phosphorus in phosphate? Plus 5. Okay. Sulfur in thiosulfate. This is called thiosulfate ion. How about that? Right? Thiosulfate, sulfur. Can someone tell me? Plus 3. Plus 6. You're not sure? Right? Okay. Why? Because I believe, I will come and check. I believe none of you drew this structure correctly. I'll come and see. Carbon. What is the oxidation state on carbon? What is the oxidation state on carbon here? Plus 2. Right? Let's see. We'll see. So, shall we do them now if you have already done it? I believe, while I was explaining also some of you were doing it, which is not ideal, but we'll quickly get that done. Anyone wants to copy it down? Already done? I'll give you a minute. Okay, I'm going to start now. Everyone pay attention here. Phosphate. Phosphorus is the least electronegative, so it's in the center. And there are 4 oxygens connected to phosphorus. So it looks like this, students, the Lewis structure. Students, now you are at a level where you understand how the Lewis structures are drawn. Each of these have lone pairs, but going forward, I wouldn't necessarily draw the lone pairs because it's a bit time consuming when I'm trying to explain. You have gotten to the correct structures as far as I checked. Everyone has gotten to the correct structure, which is good. So this is the phosphate ion, polyatomic ions Lewis structure. So again, compared to phosphorus, oxygen is very electronegative. So therefore, bond electrons are going more towards oxygen. Which makes oxygen minus 1, phosphorus plus 1. Same applies to all the bonds. Minus 1 plus 1, minus 1 plus 1, minus 1 plus 1, minus 1 plus 1. Is that clear? You understand? So now, phosphorus has 5 positive charges around it. So therefore, phosphorus's oxidation number is plus 5. Each time we see oxygen, we normally see oxygen happens to be minus 2. Here all the oxygens are minus 2. Right? This oxygen also is minus 2, where you can very clearly see. Okay. Now the thiosulfate ion. Out of oxygen and sulfur, sulfur is the least electronegative. So when you are choosing a central atom, that should be considered. Least electronegative element is the central atom. So sulfur is the central atom here. All the others are connected to this sulfur. That means the additional sulfur we have over here is also connected to this sulfur. Then you do your Lewis structure thing, like where you write the number of electrons and the bond electron pairs, and then the number of valence number of lone pairs you need to distribute. So once you do that, you get to a structure that looks like this. Right? So these are formal charges actually. I should have drawn them in black itself so that it's identifiable as formal charges. Is that clear? So this is the main way in which you should draw thiosulfate ion. So now pay very close attention here. This is a good one. So sulfur and oxygen over here. Again, sulfur is less electronegative than oxygen. So oxygen gets the electrons. So this bond, this side of the bond is minus and this other side is plus. So sulfur gets plus, oxygen gets minus. So that applies to all of these bonds. Plus, minus. Plus, minus. But that only applies to oxygen sulfur bonds. Now if you take sulfur and sulfur, is there an electronegativity difference between two sulfur atoms? No. Between two sulfur atoms you don't necessarily have an electronegativity difference. So therefore students, you don't have a charge separation here. You don't say this one is plus, this one is minus. You don't say anything like that. Is that clear? So that means this sulfur is at 0 oxidation state. Right? Is that clear? It does not have positive or negative oxidation state. It's 0 because it is not gaining electrons or losing electrons. It is only connected to another sulfur atom which does not have a higher or lower electronegativity. Is that clear? So we consider this to be 0 in oxidation state. This sulfur over here has 1, 2, 3, 4 positive charges. So therefore its oxidation state is plus 4. Is that clear? And all the oxygens happen to be minus 2 each. Okay? Right. Done? Now cyanide. I believe still some of you are trying cyanide, right? Okay, let's see. If you take carbon has 4 valence electrons. Nitrogen has 5 valence electrons. Minus 1 charge. Minus 1 charge has 1 additional electron added to this. Altogether the total electron number happens to be 10 electrons. That means electron pairs would be 5. Right? There should be 5 electron pairs. So the addition of, guys listen up, addition of lone pairs and bond pairs should be 5. Carbon connected to nitrogen. Carbon is less electronegative, so in here we don't necessarily have a central atom, but let's say carbon is the less electronegative one, so therefore we start with carbon. There's 1 bond electron pair that is already gone, so we have to now deal with 4 other electron pairs. We can start distributing them starting from nitrogen. Nitrogen gets 3 just to complete its octet like this. The additional electron is given to carbon. Now if you take a look at their formal charges, nitrogen should have only 5 electrons, but nitrogen has 6 here and 1 in the bond. 6 here and 1 in the bond. Altogether 7. So what is the formal charge of nitrogen? -2, which is not good, right? Now carbon should have altogether 4 electrons, valence electrons, but it has 2 here and 1 here. It is missing 1, so it has +1. So what happens here is, students, these lone pairs are converted into bond pairs. When that happens, carbon's +1 goes away, nitrogen -2 goes, and it becomes -1. Now some of you stopped here thinking, this is okay. But the thing is, although nitrogen is completing its octet, carbon is not. Do you see? Nitrogen has 2, 4, and these 2 bonds, altogether another 4 electrons, altogether 8 electrons around nitrogen. But carbon has 4 electrons here and 2 here. 6 only. That is not stable for carbon. So this bond is converted into another, so this lone pair is converted into another bond pair like this. Right, we discussed this under lone pair, so dative bonds. We said that lone pair is donated as a dative bond. So now, at that point, this negative charge on nitrogen will disappear, because nitrogen now has 1, 2, 3, that means 3 electrons in each of these bonds, and 2 more electrons here. Altogether nitrogen has 5 electrons. That belongs to nitrogen, and nitrogen should only have 5, so there's no charge on nitrogen. If you take carbon, it has 1, 2, 3 electrons on carbon in the bonds, and then 2 other electrons here, altogether 5. Carbon should have only 4 valence electrons, but this has 5, therefore carbon is minus. Is that clear? So therefore the negative charge is on carbon. This is the Lewis structure of this particular molecule, not molecule, ion. Nitrogen is more electronegative than carbon, so each of these bonds, -1 on this side, +1 on this side, +1, -1, +1, -1. So on nitrogen side, the total charge is -3. Carbon side, there are +3, but there's 1 minus here, +3 and 1 minus, so therefore +2. Is that clear? You understand now? Okay, everyone. So this is how formal charges, not formal charges actually, this is how oxidation numbers for polyatomic ions as well as molecules, polyatomic molecules are found out. There's another easier shortcut method which is somewhat less accurate than this. We will be talking about that after the break. Okay? So we'll have a small break and we'll start the class again at 5:15. Alright, I'll see you at 5:15. Right, everyone, we'll start. So the next part is basically going through the rules. So we'll quickly go through all the rules when it comes to deciding oxidation number using another specific method. So turn to page number 2. There are some rules given to you. Read those rules. I will explain them one by one. The very first one says, in free elements, each atom has an oxidation number of 0. For example, H2Br2, Na, beryllium, potassium, oxygen, phosphorus, all have oxidation numbers of 0. Any element means something that is consisting of only the same type of atoms, right? So therefore between them there is no electronegativity difference. Any element has 0 oxidation state. So highlight that free elements has an oxidation number of 0. Underline or highlight that, that is important for the next method that we are going to use. In the next method that we are going to discuss, this is important. Then the next one, for monoatomic ions, their charge is the oxidation number itself. Very easy. Underline that as well. The very first sentence of the second point. Underline that. And the next one is important. Oxidation number of oxygen in most compounds is -2. In most compounds -2, but in peroxide or hydrogen peroxide and peroxide ion, it is -1. Superoxide, it is 0 and -1. Peroxide and superoxide, students, it's going to have a different oxidation state. Peroxide and superoxide, it's going to have a different oxidation state. Something to keep in mind. Is that clear? So when it comes to peroxide ion, it's something that looks like this. You have basically something like this going on. So each oxygen is going to be having -1 charge on it. So this is called the peroxide ion. O2 2-. So you see some metal peroxides are there, right? Some, like you are very familiar with hydrogen peroxide. That hydrogen peroxide has this. These are not just oxides. This is a separate category referred to as peroxide or peroxide. Is that clear? Normally you see oxides like, metal oxides like magnesium oxide, sodium oxide. Oxide ion is this. Oxide ion is this. When you just say oxide, it is O2, sorry. Oxide ion is O2-. O2-. This is oxide. Right? And these are peroxides. Is that clear? And there is another one referred to as superoxide, that is we have O2-1-. O2-1-, it looks somewhat like this. You will learn about them later when it comes to sp(d) block elements also. So we have this situation. There is one oxygen with a negative charge. The other oxygen has only 6 electrons around it. So 1 here, 2, 3, 4, 5, 6. So this oxygen has an unpaired electron here. So this is a superoxide ion, O2-1-. Is that clear? So in this particular ion, this oxygen is 0 oxidation state. This oxygen is -1 oxidation state. Is that understood? Is that clear? So over here, this one is -1. This one is also -1 when it comes to peroxide. These are called peroxide ions. These are called superoxide ions. Peroxide, superoxide. Right. Okay. Did you all go see the? Nobody. You went. Right. Can we actually take a vehicle from there? I just want to know. Right. No problem. Right. Is it crowded? Right. We'll have the class till around 8, and then okay. So do you understand this? So now, apart from these, now these are, this is the normal usual oxide ion. This is the usual oxide ion. No fancy names there. This is oxide ion. So this one has a -2 oxidation state. That one has a -2 oxidation state. Right. If you want to see the oxide ion, you have oxygen with altogether, right? Altogether 8 electrons around it like this, so it is oxide. Anyway, so apart from these peroxide and superoxide, there's another instance where oxidation number of oxygen can change. That is when oxygen is bonded to a more electronegative element than oxygen. Now in the entire periodic table, the most electronegative element is fluorine. Then comes oxygen and then comes nitrogen. So there's only one more element that is more electronegative than oxygen. That is fluorine. That no other element is more electronegative than oxygen. So if the oxygen is connected to fluorine, at that point, students, fluorine will get the -1 charge, right? Fluorine will get the -1 charge, oxygen will get the +1 charge. Is that clear? Because that means this oxygen and fluorine bond electrons are going more towards fluorine. So therefore, if the partial transfer is thought to be a full transfer of electrons, then the fluorine atom is gaining the 2 electrons from this bond. So fluorine becomes -1, oxygen becomes +1. Understood? Right. So this is something that you need to keep in mind. Now I would appreciate if you can, there's a bit of space underneath. So copy down the peroxide ion, superoxide ion, and if you want oxide ion also, but I want you to mainly take peroxide, superoxide, and the OF bond. It's not a molecule that I have drawn here, students. I have simply drawn the OF bond here, because I want to show when it comes to only OF bond, oxygen will get a +1 oxidation state. Are we done? Right. So then move on to the next point. So you can see in the next point it says the oxidation number of hydrogen is +1 except when it is bonded to metals in binary compounds. So in other words, students, again, if you observed most of the questions we did earlier, when hydrogen was bonded to carbon, when hydrogen was bonded to oxygen, or whether it was bonded to nitrogen, it usually forms +1 oxidation states. Hydrogens are always going to be +1. Right? If it is a molecule of hydrogen, 0. Right? For example, students, this is 0. Hydrogen molecule's oxidation state is 0. No problem there. But any other compound, when hydrogen is bonded to anything else, any other non-metal, if I'm being specific, any other non-metal, hydrogen is going to be +1. But there's always an exception. That is how it is. There's always an exception. When it comes to metal hydrides. Now, if you take metal, students, strong metals like sodium, reactive metals like sodium, potassium, calcium. Now these metals, they will never accept electrons. They are there to release electrons. They are dying to release electrons. That's why they are very reactive also. If you take sodium is very reactive. Why is it very reactive? Because there's one outer electrons in the outermost energy level, one electron. It is waiting to get rid of it, because if it is rid of it, then it forms a noble gas electronic configuration. So sodium is waiting to release that electron. So sodium is very unlikely to take an electron. Instead, it is always releasing electrons. So because of that, students, when hydrogen is forming compounds with metals like sodium or calcium or potassium, or in other words, we say metal hydrides. Metal hydrides like sodium hydride, let's say potassium hydride or calcium hydride. The metal is always in positive oxidation state. Calcium forms +2 ions only, so calcium is +2 here. But the hydrogen here is in minus oxidation state, -1, -1. There are two hydrogens, each hydrogen is -1. So -1 -1 is -2. So therefore cancels off this oxidation state. But whenever you are drawing a line like this and writing oxidation states, we write the oxidation state of one hydrogen atom, not both of them. 1. So one hydrogen is how much? -1. Is that clear? So this is, we write -1. So there are two hydrogens. For example, you can think of it this way: calcium 2 plus present with two hydride ions. We call this hydride ions, right? So basically, minus minus is 2 minus plus 2 plus cancels everything off, neutralizes. So it's ionic compound like this. Is it understood? So students, this is the place where hydrogen will obtain a minus oxidation state. When they are forming metallic hydrides, hydrogen is always, when they are forming metallic hydrides, hydrogen is always minus 1. In all other instances, it is not. Is that clear? Right. So now we move on to the next part. So first of all, copy this down if you have the space there. At least 2 examples. If you are copying down only 2, write sodium and calcium. Sodium and calcium. Had to be today, you know, the matrix. Right. Okay. Now, students, the last the point before the last point, that's group 7 elements. Group 7 elements, students, happen to be bit more electronegative. I would say in each individual period, the group 7 element always happens to be the most electronegative. Do you understand what I'm saying? So if you take few different periods, right? Let's say this is period 2. End of period 2, we have fluorine. We have the noble gases. I have removed noble gases because we don't normally talk about electronegativities of noble gases. Can we talk about electronegativities of noble gases? We don't, right? But if you take any period, the end of the period is usually where the electronegativity is high. I told you, as you move towards the right hand side across the periodic table, when you're moving to the right hand side, the electronegativity increases. So therefore, in individual periods, if you take each period separately, the most electronegative element is found in group 17 or halogens group. Is that clear? But another thing that you need to keep in mind is, as you go down the group, the electronegativity decreases. Is that clear? Electronegativity decreases down the group, but when you're going across a period, electronegativity increases. So fluorine is the most electronegative in the entire periodic table. Then comes oxygen, then comes nitrogen, and then followed by that we have chlorine, right? And then there are others. And then as you go down this halogen group, the electronegativities gradually decrease. Okay? So what you need to keep in mind is, most of the time when halogens, that means group 17 elements, are bonded to other elements, they tend to be more electronegative than the other elements. For example, when any of these halogens are bonded to hydrogen, compared to hydrogen, this is more electronegative. Is that clear? However, there are, especially when you go down, like bromine, iodine, acetane. Now, there are many elements that are more electronegative than iodine. Okay, But especially if any of these halogens are bonded directly to oxygen, which is the second most electronegative element, then oxygen is going to be getting minus, halogen will become plus. Okay, but in most cases halogen will become minus when it is bonded to another atom. Is that clear? Most cases, if a halogen is bonded to another atom, the chances of that atom being less electronegative than a halogen is high, right? Usually halogen is more electronegative than the other atoms, but then again, as you go down the group, halogen's electronegativity decreases. So you have to be careful, you have to be mindful, right? You have to remember the electronegativities a little bit. So, and then however, it's a clear-cut indication, except for fluorine. When any other halogen is connected to oxygen, oxygen is minus and halogen becomes plus. Is that clear? That is a very clear thing, because why? The second most electronegative element in the entire periodic table is oxygen. So all the others are less electronegative than oxygen. So the bond electrons will be attracted more towards oxygen. Oxygen becomes minus, or oxygen becomes negative. Do you understand? Right. Okay. So now the last point is the most important one. So we can find another way of finding oxidation number using this last method. In your writing books, write down another heading: alternative method for finding oxidation numbers. Alternative method for finding oxidation numbers. You can write the same sentence. You'll write down there, because otherwise when you're studying it will be problematic. You can write, in a neutral molecule, the sum of the oxidation numbers of all atoms, the sum of the oxidation numbers of all atoms, the sum, SUM, sum of the oxidation numbers of all atoms must be 0. That's point number 1. And then the next point, in a polyatomic ion, the sum of oxidation numbers must be equal to the net charge of the ion. The net charge of the ion. Under that, please write the above details can be used to calculate the oxidation number of molecules and ions, oxidation number of atoms in molecules and ions, Now let's see how this is done. Pay attention, students. We'll take two molecules that you did earlier. For example, NH3 we did, right? We also did carbon dioxide, right? And we also discussed sulfur trioxide. I want to take the same molecules because I want to show you that this method works. So now there are a few rules we discussed. What are the rules? The very first one, atoms are always, elements are always neutral. Like hydrogen molecules, bromine molecules, chlorine molecules, they are always having zero oxidation state. Right? Zero oxidation state, no other oxidation state for them. And then we learned, when it comes to oxygen is always -2 when in compounds. When in compounds, oxygen is always -2, except for 3 exceptions: peroxide, superoxide, and when oxygen is connected to fluorine. That's it. And then we learned about hydrogen. Hydrogen is always +1. You need to remember these rules. Hydrogen is always +1 except for when it is connected to a metal, forming metal hydrides. So that's a small chance. And then we learned most of the halogens are -1. Right? So based on these rules, we can decide the oxidation numbers of these. So now, hydrogen is always +1. We know that. So therefore, we can do a calculation to this. We know that this is +1. We don't know the oxidation number of nitrogen because the rules didn't say anything about nitrogen, right? So therefore, using the rules and the final sentence that you wrote there, we can find the oxidation number of nitrogen. So it says the oxidation numbers of all of the atoms added together should be equal to its charge, or in a neutral atom there's no charge, so it should be equal to 0. So nitrogen, we have X, there are 3 hydrogens, each hydrogen is +1. So there are 3 hydrogens, I multiplied +1 by 3. This should be equal to the charge. This is a neutral atom, so neutral molecule, no charge. So therefore X is equal to +3, meaning, X plus 3 is equal to 0. So therefore X is equal to -3. Right? We found out the nitrogen oxidation number earlier. Wasn't it -3? It was. Right? So this is a bit of a shortcut method. And then carbon dioxide. The method didn't say anything about carbon, so we'll say its oxidation number is X. Oxygen, what is the oxidation number of oxygen? -2 always. Right? -2. Right? So then we can say X plus, there are 2 oxygens, 2 multiplied by -2 should be equal to 0. So that means X -4 is equal to 0, meaning X is equal to +4. Right? X is equal to +4. Right? If you haven't ever been to a Chanda rally, you can now hear it. Like there's a good rally going on. Right? So is that clear now? So this sulfur, we found it to be +6 if I'm not mistaken, right? Let's find out whether we are getting the same answer here. This is -2 oxygen always. So therefore we have X plus, there are 3 oxygens, 3 multiplied by -2, which is equal to -6. So therefore, which is equals to 0, the overall charge of the molecule. Molecule doesn't have a charge here, it's 0. So the 0 indicates that this is neutral. Okay, no charge. If there was a charge, we write the charge here. There was no charge. So X -6 is equal to 0. That means X was equal to +6. So that means the oxidation number of sulfur is +6. Oxidation number of carbon is +4. Is that clear? Right. So under that, please copy this down. I'll do some questions with you in a second. For the time being, take this down. Okay. Right. So then I'll do one ion and then I'll get you to do the other ions. For example, so if you're talking about something like this, let's say we'll take carbonate, right? 2-. Now pay attention. Oxygen's oxidation state is known because the rules, they define it. rules they define it. And then carbon is the one that we don't know, it's X. So carbon dioxide oxidation state would be carbon's oxidation state would be calculated. X plus, there are 3 oxygens, 3 multiplied by -2 is equal to, that means the sum of all the oxidation numbers should be equal to the net charge of the ion. I gave you that in a sentence. Should be equal to net charge of the ion. So sum of them should be equal to -2, which is the net charge of the ion. Is that clear? So therefore this is becoming X, this becomes -6 is equal to -2. So X is equal to -2 plus 6, which is going to be +4 in oxidation state. Is that clear? +4 in oxidation state. So carbon's oxidation state is +4. Is that clear? So write down, first of all take this down, I'll give you a question after that. Write down a small question. Find the oxidation number of all the atoms in the following ions. In the following ions and molecules. Quickly do this. We have NH4 plus, right? So this is the first one. Second one, HCO3 1 minus. Third one, SO4 2 minus. Fourth one, HSO3, not HSO4, HSO3 1 minus. Fifth one is S2O3 2 minus. S2O3 2 minus. Take these 5 and answer this question quickly. If you have a question, you can ask me. Shall we discuss this now? Right, first one is NH4 plus. So again, NH4 plus, we write nitrogen, we don't know the value. Hydrogen is defined usually +1 in all compounds except for metal hydrides. So therefore, if you write this X plus, there are 4 hydrogens. So there are oxidation number of hydrogen should be taken 4 times, is equal to 0, because this not 0 actually, this one has a this is ion, it has a charge. What is the net charge? +1, right? Net charge is +1. So therefore we have X plus 4 is equal to +1. That means X is equal to +1 minus 4, which is -3. Nitrogen has a oxidation state of -3. Is that clear? Right. So yes, now we move on to the next one. I will do it here. HCO3 1 minus. So now students, hydrogen is well known to us. Hydrogen is what? +1. Oxygen is usually -2. Carbon we don't know. Carbon is X. Clear? So therefore we can write +1 plus X plus oxygen is -2, there are 3 of them. So 3 multiplied by -2 is equal to the overall charge here, which is -1. So therefore, when you write this, you can have x plus 1 minus 6 is equal to -1. So plus 1 minus 6 is -5. -5, you send it to the other side, it becomes x is equal to -1 plus 5, which means x is equal to plus 4. Is that clear? Carbon is plus 4. I'll do the next bits here. Sulfate, you have already done this. Sulfate, when you were doing it manually without having this method, what was the oxidation state of sulfur? Plus 6. Here also you get to plus 6. So you have sulfur, which you don't know the oxidation state of, let's say X. So this is the ion. Oxygen is -2. So you have X plus 4 into -2 is equal to -2. So X plus, or actually X minus 8 is equal to -2. X is equal to -2 plus 8, which happens to be plus 6. So HSO3 minus also is similar. If I do it here, we have HSO3 minus, which one we don't know is X. Sulfur is the one that we don't know about, and then oxygen and hydrogen, we know the values. So if I do the calculation here, I'll do the calculation here. We have plus 1, which is hydrogen. Sulfur is X. There's 3 oxygens, and all of them should add together to give the overall charge, which is -1. So we have X plus 1 minus 6 is equal to -1 here. So X minus 5 is equal to -1. X is equal to -1 plus 5. That means X is basically in plus 4 oxidation state. Right? Sulfur over here is plus 4 oxidation state sulfur. Is that clear? Now we come to a bit of an important part, the last one, this one. So I will erase this part because I need the space. Right? The last one is important. There is a reason I gave you that. So this method, if I use this method, S2O3 2 minus, we don't know the oxidation state of sulfur, so we will call it X. Oxygen is -2. So therefore we have X. Actually, can I just write X here? How many? Now X represents the oxidation state of sulfur, right? X represents the oxidation state of sulfur. How many sulfurs are there? 2. So if you are sticking to the rules, we have to write 2X, because oxidation sulfur is X. There are 2 sulfurs, so 2X plus 3 into -2 is equal to the overall charge, which is -2. Pay attention, pay attention. And then at that point, this becomes 2X minus 6 equals -2. 2X equals -2 plus 6. So basically 2X is equal to plus 4. That means X is equal to plus 2. Right? But is this correct? We did it manually earlier. See, using the Lewis structure, we took a look at the bonds and we did it manually. At that point, one sulfur out of the 2 was 0 oxidation state. The other one was plus 4 oxidation state. Now this method says this is plus 2. This is wrong. Is that clear? This method is wrong, because this method is a new mathematical way of getting to the answer. That method, which we manually did, was more accurate. So therefore you need to be proficient with both. But keep in mind, sometimes this method gets you to the wrong answers for oxidation numbers. Sometimes, not all the time, 99% of the time correct. But you have this type of instances. Is that clear? So if they specifically ask S1, sometimes they give you the structure and say, like, they will give you the structure and they label the atoms. Like they say sulfur here, this sulfur and this oxygen, and then they give you something like this, right? Then they will label these sulfur atoms. They will call this sulfur 1, sulfur 2. They might ask you. Now in the structure they say questions, you will come across those. They will ask you what is the oxidation state of this sulfur and this sulfur. This sulfur is 0. Sulfur 1 is 0. Sulfur 2 is plus 4. Is that clear? But if you just randomly use this equation and get to sulfur's oxidation state as plus 2 and you write plus 2 here, you are wrong. Is that clear? Because one sulfur is definitely 0, the other one is plus 4, not plus 2. Is that clear? So what you get here is plus 2 is the averaged out version. This one was plus 4, this one was plus 0, this one was plus 4, this one was 0. So the averaged out value is plus 2. That's what you are getting. Right? So sometimes this method can get you to the wrong answer. And sometimes you can't get to the answer at all. For example, cyanide. I give you cyanide. Can you find the answer? Rules don't say anything about nitrogen. Rules don't say anything about carbon. Can you find the answer? No. Right? Some you can't do. Is that clear? Right. So others you can, like for example, another one just before we wrap it up, something like for example CHCl3. Now we learned according to the rules, halogens are usually -1. So this one is -1, this one is +1. We don't know carbon because carbon's oxidation number can change based on the compound. So if I do this, we have x plus 1 plus 3 into -6. So 3 into -1 is equal to 0. That means x plus 1 minus 3 equals 0. So -3 plus 1 is -2. X is equal to +2. When you send -2 to the other side, it becomes +2. Is that clear? So this one was correct. In your previous manual method also, you got to the same answer. When you're drawing Lewis structure and doing it, you got to the same answer earlier. Is that clear? Right. I would actually prefer you taking this down because I didn't give you any examples with halogen in it. Because we need to know halogens are -1 most of the time. Okay, so now students, today we finished the oxidation number part. Basically how to identify the oxidation number of any element is now done, or any atom in a compound is done. That is very crucial going forward. If you don't have a good understanding of this, it will be problematic. So that's why we took the time to finish it off. So next week we talk about reactions. When it comes to reactions, how the oxidation number changes, and then we move on to naming compounds. Very important. Again, naming compounds, most of the students don't have a good solid background in it. So I want you to have that background moving forward. So we will talk about naming compounds. We learn about traditional and as well as UPAC naming system. Okay, so next week we will finish that part off. Right everyone, so we'll stop the class here and I'll be seeing you all again next week at the same time.